We present USHER, Unbiased Sampling for Hindsight Experience Replay. HER is a sample-efficient method for multi-goal reinforcement learning. It works by treating failed trajectories to one goal as successful trajectories to a different goal. This increases HER's sample efficiency, but also incurs a survivorship bias in HER's value function. This survivorship bias appears because repurposing failed trajectories like this means that HER is training almost exclusively on successful trajectories. This gives HER a tendency to overestimate its likelihood of success when taking risky or stochastic actions. One concrete example of this bias involves a robot with two possible paths, a dangerous short path and a safe long path. HER overestimates its likelihood of safely traversing the dangerous path and chooses this dangerous short path instead of the long safe path. This kind of bias appears in physical robot experiments as well. In this situation, a robot is tasked with navigating to a target location in the presence of a partially known set of obstacles. Repeatedly trying to go through the center succeeds only a small fraction of the time. However, HER overestimates this likelihood of success. This leads HER to repeatedly fail. In contrast, USHER learns to accurately gauge risk and learns to avoid taking unnecessary risks, such as repeatedly running into obstacles. It always attempts to go around the obstacle in the middle when it is present, and never bumps into it more than once. When USHER does fail, it is due to sim-to-real transfer problems that would be equally challenging for any algorithm that does not have access to data from the real robot. We propose two major changes to HER. First, we separate the goal used for the policy from the goal used for the reward. Only the reward goal is sampled using HER. Secondly, we learn a probability distribution over the robot's future achieved goals, and use this distribution to perform important sampling on the loss. This allows us to recover the true unbiased value function. Our derivation is as follows. We can represent the Q function as an expected value of the current reward plus the next value conditioned on the current state and the current action. However, we run into a problem here when using HER. As we mentioned previously, the reward goal in HER is sampled from the future distribution of states. This means that the next state, S prime, and the reward goal, GR, are not independent, which changes the expected value. We need to find a way to decouple S prime and GR while still using HER. We do this by reformulating the probability of S prime when using HER. Observe that the probability of seeing a next state, S prime, conditioned on the state, action, reward goal, and policy goal, can be decomposed using the conditional probability rules. This gives us the following identity. We can then use three tricks to simplify this expression. First, we observe that the reward goal is sampled from the future trajectory of the current state S. By the Markov property, we know that the future trajectory depends only on the most recently observed state. Since GR is conditioned on S prime in addition to S and A, this means it is independent of S and A. Next, observe that unlike the reward goal, the policy goal is not sampled from the future trajectory of S. It's sampled at the start of each episode and does not change at training time. This means that it is independent of the state transition distribution, and the probability of S prime does not depend on it, but only upon S and A. Lastly, we assume that we have a deterministic policy, and the policy's action is fixed given the state, and conditioning on it does not change the probability of a future trajectory, nor does it change the probability of sampling GR. Together, this gives us an expression for the probability of observing a given state transition when using a given hindsight goal, in terms of the environment's original state transition probability. However, now we can make an interesting observation. Observe that the probability of selecting a state GR conditioned on S, A, and G pi is effectively a successor representation, because the reward goal, GR, is drawn from the future trajectory of S. This means that it is effectively a future state occupancy measure. Therefore, we can learn these just like we learned the Q function. This brings us to the core idea of USHER. HER's bias is effectively a ratio of successor representations. Therefore, we can learn a successor representation to debias the Q function. But most interestingly, this successor representation can also use HER, and we can use it to importance sample its own loss function. This allows us to achieve much greater sample efficiency than we would be able to do otherwise. On the same toy environment as before, we find that USHER learns to avoid the dangerous region and take the long but safe path to the goal, achieving a much higher success rate and average reward. We challenge both methods to drive a car while subject to various kinds of stochasticity. In one environment, they must avoid obstacles, while the steering function is subject to a varying random noise. And secondly, they must learn to navigate a traffic light where running a red light has a risk of collision. In the noise environment, HER learns to cut corners much closer and as a risk crashes the car much more frequently. On the red light environment, HER learns that it is safe to run the red light, while USHER learns that it is safer to wait for a green light. On an array of deterministic robotics tasks, we find that USHER is able to keep pace with HER. On each of the 3 simulated fetch robot tasks, USHER is able to match HER's performance, even though there is no stochasticity there to cause HER to learn an incorrect value function. We additionally create an environment to test USHER's performance at stochastic high-dimensional robotics tasks. We consider a robot arm mounted on a mobile base, tasked with moving a ball to a goal. Additionally, a random wind force can potentially blow the ball off course. We find that USHER learns to carefully place the ball at the goal, while HER throws it and frequently misses. As a result, USHER performs significantly better than HER. This is due to its ability to accurately assess the risk of dangerous actions like throwing the ball. Lastly, we test both methods' performance on physical robots after being trained to transfer from simulation. The robot must learn to navigate an environment with incomplete information about what obstacles are present. In the simulated environment, USHER learns to avoid obstacles, while HER repeatedly runs into them. On the physical robot, this behavior is replicated. HER tries to drive directly through the obstacle, while USHER learns to navigate around it, and succeeds more often as a result. In conclusion, we find that HER suffers bias in stochastic environments. USHER is able to correct for this bias without sacrificing HER's sample efficiency or low variance. We show that this method is effective across a wide range of robotic tasks. Thank you.